When you build a traditional software, there is this fundamental contract between you and the machine.
Right, yeah. A highly deterministic contract.
Exactly. Like if you query a relational database for a user ID that just doesn't exist, the system doesn't, try to guess their name to make you feel better.
No, it definitely doesn't.
It just returns a null value. It throws an error. I mean, it fails loudly and it fails predictably. And as engineers, we rely heavily on that strict determinism.
We really do. You build your entire architecture around it.
Right. Your error handling, your monitoring, all of it is built around the comfort of the stack trace and the good old 404 error. But stepping into the world of generative AI means basically tearing that contract to pieces.
Oh, absolutely. It's a complete paradigm shift.
Because you are dealing with a system that, instead of crashing when it hits a gap in its knowledge, will literally just look you dead in the eye and hand you a beautifully formatted, syntactically perfect, absolute lie.
Yeah, you're migrating from a deterministic architecture where, a specific state and input always yield a specific output to a probabilistic one.
And that transition is jarring.
Very jarring for anyone whose muscle memory is built on strict logic gates and, definitive try-catch blocks. So, welcome to the deep dive. Tonight, we are analyzing one of the most persistent architectural challenges in modern technology.
Yeah, if you are an engineer or a system architect or just a developer trying to integrate large language models into your stack right now, you are undoubtedly wrestling with this.
It's everywhere.
It is. Our source material today is drawn from the LLM Mastery series, specifically their technical breakdown on why these models confidently fabricate information.
The hallucination problem.
Right. So the mission for this deep dive is to unpack the underlying mathematical mechanics of why hallucinations happen. And, more importantly for the builders listening, how we actually engineer defensive systems around them.
Yeah, and to engineer around the problem, we first need to clearly define what a hallucination actually is at the system level.
Let's do it.
So the source material categorizes them through three specific parameters. They are highly fluent, they are output with high statistical confidence, and they are factually entirely false.
Right. So we aren't talking about a model spitting out garbled Unicode characters or broken syntax.
No, not at all. It looks completely normal.
The failure modes are actually fascinating to look at from a debugging perspective. Like, you see fabricated citations, right, where the model generates academic papers that just do not exist.
But it constructs them with perfectly valid DOIs and plausible author names.
Exactly. And you get entity confusion where it merges the parameters of two completely different software libraries.
Oh, that's the worst.
It is. And the hardest one to catch is just plausible-sounding nonsense. It adheres so strictly to the expected syntax and tone that your brain or, your parser just accepts it as valid data.
And that plausibility is exactly what makes it a systemic risk. I mean, if the output was structurally malformed, a basic regex or a schema validator would catch it instantly. But to fix this in a production application, we have to look under the hood at the core mechanism. The root cause here is that larger language models are optimized for plausibility, not objective truth.
Right. They operate almost entirely on next token prediction.
Yes.
Yep.
They're prediction engines.
So let's unpack the mechanics of that for the developers listening. I try to think of it like an incredibly fast, highly skilled improv actor.
Oh, I like that analogy.
Right. Like you pass a prompt to an API endpoint, and the model isn't executing a strict lookup against a verified database of facts. It's playing an improv game where the only hard rule is keep talking and sound good.
Yes, but for syntax.
Exactly. Yes, and. It maps the sequence of input tokens and calculates a probability distribution over its entire vocabulary for what the very next token should be.
Yeah, based on the statistical weights established during its pre-training phase. So it's essentially calculating logits. Those are the raw, unnormalized predictions.
Yeah.
And then it passes them through a softmax function to generate probabilities.
Yeah.
When it builds a response, it is iteratively asking itself one mathematical question over and over.
Which is?
Given this specific sequence of preceding tokens, what is the highest probability vector for the next token?
Wow. So the model has literally no internal epistemology.
None. It doesn't have a database of true and false flags.
Yeah.
It only possesses this multi-dimensional map of statistical relationships between token embeddings.
It's just math. It's not malicious. It's not lying to you on purpose.
Right. It's successfully completing its core objective, generating the most mathematically plausible next word, regardless of factual accuracy.
Which leaves us in a really strange spot architecturally. I mean, if the model just got things wrong occasionally and returned an error code, we could build simple error handling.
Oh, easily.
We implement retry logic and circuit breakers all the time in software. But the real danger lies in how it presents those errors. The source refers to this as the confidence problem.
And this is arguably the most critical vulnerability when deploying these systems. An LLM's next token prediction engine generates a factual statement with the exact same declarative sentence structure as a complete fabrication.
Right, they sound equally certain when they are right and when they are entirely wrong.
Exactly.
Yeah.
Because there is an absence of epistemic uncertainty in the model's architecture. It just doesn't know what it doesn't know.
Because knowledge isn't stored as discrete record.
Right, it's a continuous distribution of weights.
Man, bringing this back to an engineering perspective, if I ping a REST API and the endpoint is deprecated, I get a 410. Gone.
Yep.
If I try to insert a string into a Boolean column, my ORMM throws a type error. I can write a try-catch block for that. I can fire an alert to Datadog.
You have a signal.
Exactly, I have signal. But if I ask an LLM to extract data from a document and format it into a JSON payload, it might return a flawlessly formatted JSON object.
Oh, completely flawless.
The keys match my schema perfectly. The brackets are closed, the syntax is totally valid. But the values inside those keys might be a completely hallucinated user profile.
And from the perspective of the executing code, the API call returned a 200 OK.
Right. The parser deserializes the JSON successfully, and that poisoned data just flows silently into your downstream systems.
It's terrifying because there is absolutely no internal signal, no metadata flag attached to the token saying, hey, this probability was low, or I'm totally guessing here.
So standard debugging and error handling paradigms just don't work.
They fail completely. You cannot rely on the component to self-report its failure state.
Yeah.
We need a totally different approach.
Which means we have to treat the LLM not as a trusted data store, but as a fuzzy reasoning engine.
Exactly.
And because we lack that reliable internal signal from the model, we have to surround it with external scaffolding. This brings us to the mitigation toolkit outlined in the source.
Yeah, treating hallucinations requires a defense in-depth strategy. It's an engineering-level mitigation.
Okay, let's unpack this toolkit. The source details 3 main approaches, right?
Yes. The first and currently most prevalent architectural pattern for this is RAG, retrieval augmented generation.
RAG. You hear that acronym everywhere right now.
You really do.
Yeah.
And the core principle of RAG is shifting the model away from relying on its internal pre-trained parameters and forcing it to ground its generation in specific retrieved documents.
I look at RAG as a complete inversion of traditional software architecture.
How so?
Well, usually you bring the data to the logic, right? You query a database, get the payload, and run it through your deterministic functions.
Right.
But with RAG, you are bringing the logic to the data. You're treating the LLM's attention mechanism as a localized reasoning processor. But you first have to find the right data to feed it.
Which is where vector databases come into play. In a typical RWAG pipeline, you take your factual documents, say your company's internal API documentation, and you run them through an embedding model.
To convert the text into high-dimensional vectors.
Exactly. Then, when a user submits a query, you embed that query into the same vector space, find the document chunks that are mathematically closest, and inject them into the prompt.
And you explicitly instruct the model, answer the user's query using only the provided text.
Right. And mechanically, this heavily biases the transformer's attention heads. You are effectively overriding its memory with immediate transient context.
So that's layer 1, grounding the model. What's the second technique in the toolkit?
The second is fine-tuning for factuality. While RAG is an inference time solution, fine-tuning intervenes during the model's actual training phase.
Okay, so messing with the weights directly.
Yes. The goal here is to explicitly teach the model to recognize its own flat probability distributions and instead of guessing, output a specific sequence of tokens. I don't know.
Okay, wait, let me get this straight.
Go ahead.
We spend tens of millions of dollars in compute, right? Pre-training a model on massive GPU clusters, explicitly optimizing it to predict the next word at all costs. We build the ultimate guessing engine.
Yep, that's base training.
And then we have to spend millions more in compute fine-tuning it to intentionally not predict the next word, just to teach it to say, I don't know.
Yeah, the irony is pretty heavy there.
That is wild.
It is wild, but it highlights the reality of deploying AI. These base models are untamed document completers. These mitigations aren't cures. They are guardrails to manage a system that is fundamentally eager to confabulate.
Wow. Okay, so we have R, we have fine-tuning. What is the third tier of this defense-in-depth strategy?
Chain of verification. This one is purely a system design pattern.
Mhm.
Instead of accepting the first output the model generates, you orchestrate a multi-step workflow to force self-correction.
Having the model self-check its own claims before outputting them.
Exactly. It generates a draft, extracts all the factual claims, generates independent verification questions for each claim, answers them using external tools, and then revises the draft to strip out the hallucinations.
Okay, as an architect, listening to that workflow just triggers immediate latency alarms in my head.
Oh, absolutely.
I mean, chain of verification means I am executing 3, maybe 4 separate network calls to the LLM for a single user query. If a standard generation takes 2 seconds, this workflow might take 10.
And you're quadrupling your API costs.
Exactly. For a background batch process, sure, that's fine. But for a synchronous user-facing application, 10 seconds of latency is an eternity.
The trade-offs are definitely steep. You are trading compute, latency, and cost for a higher degree of factual certainty. But that tension is the reality of AI engineering right now.
Yeah, you have to decide where on that spectrum your specific application lives.
Right. A medical triage tool requires chain of verification. A creative writing assistant does not.
And this raises the ultimate question that the source material touches on. If managing this architecture is so expensive and complex, why not just patch the core model?
What do you mean?
Like, why don't researchers just tweak the underlying math so the model fundamentally never hallucinates at all? Just turn off the hallucination switch.
Well, because that assumes hallucination is a bug in the code. And what the AI research community has realized, and what the source highlights as this really profound conclusion, is that hallucination may be a fundamental feature of how generative models work.
Wait, really? A feature?
Yeah, the architecture isn't broken. It's doing exactly what the math dictates.
Huh.
Think back to the latent space we discussed earlier.
Yeah.
The model navigates this multidimensional space, calculating probabilities and finding novel connections between token embeddings.
Right.
The exact same mathematical mechanism that enables it to be creative is the exact mechanism that enables confabulation.
Oh, I see what you're saying. So the very thing that allows an LLM to write like a clever poem about debugging code in the style of Shakespeare.
Which we love.
Right, which we love. That is the exact same mathematical traversal mechanism that makes up a fake legal precedent, which we hate.
Exactly. You cannot simply turn off the hallucination switch without simultaneously turning off the model's ability to be creative, flexible, and generative.
Because the model doesn't classify prompts into creative or factual buckets internally, it only executes next token prediction.
Yes. If you completely constrain its probability distribution so it can only output exact matches from its training data, you eliminate hallucinations entirely.
But you also destroy the generativity. You break the very mechanism that makes generative AI useful to us.
Exactly. You essentially downgrade this complex, adaptable reasoning engine back into a really inefficient relational database.
Which brings us full circle. That's why the engineering community has to rely on mitigations like RAG and chain of verification.
Right. You manage the system at the architectural layer. You don't attempt to rewrite the physical laws of the latent space.
So dealing with hallucinations is fundamentally about management, not eradication. You architect your software under the strict assumption that the AI component will eventually attempt to pass bad data.
And you implement the necessary safety nets to catch it before it corrupts your state.
It demands a total shift from deterministic engineering to probabilistic engineering.
It really does.
Yeah.
And, as the source material teases at the very end of this module, hallucination is actually just one symptom of a much deeper, more fundamental challenge.
The alignment problem.
Exactly. How do we make AI systems actually do what we want them to do?
Yeah.
How do we ensure they are not just capable, but helpful, harmless, and honest?
Getting a mathematical optimizer to be honest is difficult enough, as we've spent this entire deep dive exploring.
Seriously.
But defining and enforcing helpful and harmless requires encoding highly subjective human values into a loss function.
It pushes system architecture directly into the realm of philosophy.
It really does. Which leaves us with a pretty provocative thought to consider.
Let's hear it.
Let's project 5 or 10 years into the future.
Yeah.
Imagine the research community actually develops a perfect mitigation technique, like a structural change that unequivocally forces an LLM to be 100% grounded and verifiable at all times.
Okay.
It completely loses the ability to guess or fabricate. Do we risk inadvertently sterilizing the very intelligence of the system?
Oh, that's interesting.
Right, like by removing the probabilistic leaps that cause hallucinations, Do we strip away the lateral problem solving that made these models so powerful for software engineers in the first place? Is a perfectly honest AI just a really expensive search engine?
Wow. Yeah, we want the absolute certainty of a deterministic system, but we demand the adaptable magic of a probabilistic one.
Can we have both?
Finding out if those two properties can coexist in a single architecture is probably the defining engineering challenge of our generation.
Definitely something to ponder the next time you are staring down a completely fabricated, flawlessly parsed JSON payload in your logs.
For sure.
Well, thank you for joining us on this deep dive. Keep building, keep analyzing the stack, and we will catch you next time.